In the previous video, we introduced the additive and multiplicative groups of integers modulo n. In this video, we're going to present more important facts about these groups. These groups are naturally occurring objects in many problems in group theory, so it's important to make sure that you understand the ins and outs of how to efficiently perform calculations in them. I'm going to talk about 4 collections of important results, and these are all things that I'm going to present without proof for now. Some of these results are things that we'll come back to and prove later, but because they come up so often in so many places in mathematics, it is important for you even at the beginning stage here just to know that they're true. The first result has to do with the cardinality of the group z mod nz times. We'll denote the cardinality of this group by phi of n, and this function is commonly referred to as the Euler phi function. Remember, z mod nz times is just the collection of primitive residue classes modulo n, so the cardinality of this group is the same as the number of integers from 1 to n which are relatively prime to n. Well, if you can factor n as a product of distinct prime powers, then there's a nice formula for phi of n. Let's suppose that n is p1 to the alpha 1, p2 to the alpha 2, pk to the alpha k, where p1 to pk are distinct primes, and the alpha i's are natural numbers. Then the Euler phi function of n is given by the formula p1 minus 1 times p1 to the alpha minus 1, pk minus 1 times pk to the alpha k minus 1. This is kind of a long formula, so I prefer to write it in product form as the product I equals 1 to k of pi minus 1 times pi to the alpha I minus 1. Now there are a couple of things that I'd like to note here, and the first is that if I factor out an extra factor of pi from each one of these pi minus 1 terms, and then gather together all of the prime powers inside of this product, I'll just get n back, and inside the product I'll be left with factors of the form 1 minus 1 over pi. This means that I can also write phi of n as n times a product over all primes dividing n of 1 minus 1 over p. One convenient thing about this formula is that I can write it down without having to label the primes in the prime factorization of n. A second important fact here, which you can derive immediately from this formula, is that if m and n are two relatively prime natural numbers, which remember means that the GCD of m and n is equal to 1, so that they don't have any common prime factors, then phi of mn is equal to phi of m times phi of n. One thing that you need to be careful of, though, is to realize that this formula doesn't hold in general if m and n are not relatively prime. So if the GCD of m and n is greater than 1, then it's not true in general that phi of mn is equal to phi of m times phi of n. Let's do a couple of quick examples before we move on, just to make sure that you understand these formulas. We're actually going to have a lot of other examples later in the video. One of the simplest cases here is when p is a prime. In that case, all but one residue class modulo p is a primitive residue class, and the formula for phi of p tells us that it's equal to p minus 1. Now let's try an example with an actual number. So if n is 9,000, what is the cardinality of the multiplicative group z mod nz times? Well, to answer that question, first let's factor n, which is pretty easy to do in this case. And then let's use the formula for phi of n, and this time we'll use the formula that says phi of n is n times the product over primes dividing n of 1 minus 1 over p. The primes dividing n in this case are just 2, 3, and 5, so it's pretty easy to work out what this number is, and we find out that phi of n in this case is 2400. The second of the 4 collection of important facts that I want to talk about in this video are Fermat's theorem and Euler's theorem. Now, in this context, Fermat's theorem is often referred to as Fermat's little theorem, not to be confused with Fermat's last theorem, which is another much more difficult result in number theory. Well, what Fermat's little theorem says is that if p is a prime number, and if a is any integer which is not divisible by p, then a to the p minus 1 is always equal to 1 modulo p. The condition that p doesn't divide a here is important, because if p divides a, then obviously the left-hand side is 0 mod p. But if you want to, you can include that possibility in the statement of the theorem by saying that for any integer a and z, when you compute a to the p, you get a mod p. That implies the statement of Fermat's theorem that I've written here, and it also covers the case when p divides a. Now, I'm stating Fermat's theorem this way because I want to compare it with Euler's theorem here in just a minute. Before we look at Euler's theorem, though, let's see an example of how to use Fermat's theorem. Let's suppose that we want to compute 43 to the power 2023 modulo 103. Now, of course, you could just say that the answer is 43 to the 2023 modulo 103. So to make the problem more precise, let's suppose that I'm trying to find a representative for this residue class, which lies in the range from 0 to 102. To make clear what the rules are here, you are allowed to use a basic calculator, but my calculator definitely won't be able to compute a number as large as 43 to the 2023. So we're going to have to use the fact that we're working modulo 103, and we're going to need to use some tricks to keep the calculations involved small. The first thing that we want to do here is to observe that since 103 is prime and doesn't divide 43, Fermat's theorem tells us that 43 to the power 102 is equal to 1 modulo 103. If we then write the exponent 2023 as a quotient times 102 plus a remainder, we can use properties of exponents to deduce that 43 to the 2023 is 43 to the 102 to the 19th power times 43 to the 85. But since the quantity inside the parentheses here is 1 modulo 103, this expression is just 43 to the 85 modulo 103. Now we've reduced the exponent by quite a lot, but 43 to the 85th power is still a huge number. When I try to put it into my calculator, it just says overflow error, and so we still have a little bit more work to do. So we want to compute 43 to the 85th modulo 103, and there are many ad hoc ways of doing these kinds of problems. But I'm going to show you a method called the square and multiply algorithm, which always works, and which is one of the fastest algorithms for doing these computations with large numbers. This algorithm also works for other types of exponentiation problems, like, for example, raising matrices to powers. And so it's definitely worth learning. The first step in the square and multiply algorithm is to write the exponent in base 2. In other words, to write it as a sum of powers of 2. Once that's done, what you want to do next is to successively square the base, 43, until you get up to the highest power used in the base 2 expansion of the exponent. So to show you what I mean, first you compute 43 to the 1, which of course is 43 mod 103, and then you square that to compute 43 squared, which, using my calculator, is negative 5 modulo 103. Then you square that to compute 43 to the 4th, and using the answer from the previous step, that comes out to just be 25 modulo 103. And then you keep going, each time squaring the result from the previous step, until you get up to the highest power of 2 that you need in order to make the base 2 expansion of the exponent. Once this is done, what we want to do is to again use the properties of exponents and multiply together all the powers of 43 in this list which correspond to the non-zero digits in the base 2 expansion of the exponent. To see what I mean, we said that 85 is 64 plus 16 plus 4 plus 1, and we computed by our successive squaring on the previous step all of these powers of 43 modulo 103. So now if we just insert the answers from the previous step into this product, then again, using our calculator, we find very quickly that this is equal to 57 modulo 103. That finishes this problem, and we conclude that 43 to the power 2023 is equal to 57 modulo 103. This is a good example of how to use the square and multiply algorithm, and it's one that I think you should have in your toolkit. Now, Fermat's theorem is great when you're trying to solve exponentiation problems modulo a prime number. But when the modulus is not a prime number, then it doesn't tell you anything. And to deal with situations like that, you need to use a more general theorem called Euler's theorem. What Euler's theorem says is that if n is any natural number, and if a is any integer which is relatively prime to n, then a to the power phi of n is equal to 1 modulo n. Phi of n is of course the Euler phi function again, and I want to mention that the hypothesis that a and n are relatively prime is absolutely essential in the statement of this theorem, so it's something that you shouldn't overlook. Now, I'm going to give you a couple of examples of how to use Euler's theorem, but before I do that, I'd like to make two comments. The first is that when n is a prime number, phi of n is just n minus 1, and the condition that the GCD of a and n is 1 is the same as the condition that n doesn't divide a. And so in that case, the statement of Euler's theorem reduces to the statement of Fermat's theorem. The second comment here is that Euler's theorem is really a special case of an even more general result, which can be applied to any finite group. What that result says is that if G is any finite group, which I'm assuming here is written multiplicatively, then if you pick any element little g of the group and you raise it to the power of the order of g, you always get the identity element. This statement is an easy consequence of what's called Lagrange's theorem, which is a theorem that I've mentioned in a previous video. When you apply this statement in the special case when G is the multiplicative group of integers modulo n, you recover precisely the statement of Euler's theorem. Anyway, you don't need to try to think too much about this result now, but this is just to show you where Euler's theorem sits in the larger context of group theory. I'm going to give you two examples of how to use Euler's theorem, and the first one is a pretty routine example. If you've done contest math in the past, you've probably seen examples like this. So how can we find the units digit of the number 43 to the power 2023? Well, first of all, finding the units digit of this number is the same as figuring out which residue class from 0 to 9 it's equivalent to modulo 10. So we want to work modulo 10, and we also need to check that 43 and n are relatively prime, which they are in this case. Since n is 2 times 5, it's straightforward to compute that the Euler phi function of n is equal to 4. So Euler's theorem tells us that 43 to the power 4 is equal to 1 modulo 10. Well, now, similar to what we did before, we want to take the exponent 2023 and write it as a quotient times 4 plus a remainder. And then we want to use properties of exponents to isolate the 43 to the fourth piece, which we know is equal to 1 mod 10. Hopefully you noticed in our square and multiply example that it's advantageous whenever possible to reduce all of the numbers that we're working with, modulo the modulus, to make them as small as possible. Therefore, instead of 43 cubed, I'm going to observe that 43 is 3 mod 10, and so I'm left at this point with just having to compute 3 cubed modulo 10, but 3 cubed is 27, so this is 7 mod 10, and now I can conclude that the units digit of 43 to the power 2023 is a 7. Now, I'd like to try to give you a more interesting example. So for the next example, let's try to compute the tens and units digit of a famous number called Graham's number. In case you've never heard of Graham's number, it's one of the biggest numbers ever used in a mathematical proof, and it can be written as 3 to the power, 3 to the power, 3 to the power, and so on. You're probably wondering how many 3's there are in this power tower. Well, it's such an astronomically huge number of 3's that it's hard to even imagine. And so instead of trying to describe it more precisely than that, let's just say that we're not going to run out of 3's when we're doing this calculation. I'd like to tell you more about the definition of this number, but it would take a long time, so let's just stick with this for right now. Now, one thing to be careful about with this definition, and this is probably something that your teachers told you when you were learning about properties of exponents, the number that I've written here is not the same thing as 3 to the 3 in parentheses to the 3 in parentheses to the 3, and so on. This is really a power tower of 3's, and so just keep that in mind when we're doing the calculation that follows. If we were just trying to find the units digit of Graham's number, then we would want to know what it is modulo 10, and that is actually a lot easier, but I wanted to make the problem interesting, so I asked here to find the tens in units digit, which means we want to know what it is modulo 100. In other words, we're trying to find a residue class from 0 to 99, which is equal modulo 100 to the number a to the b1, where a is 3, and b1 is the power tower of 3's that are sitting on top of the bottom 3 in Graham's number. Even though this is a little bit intimidating, it's not a lot different than the problems that we did in the previous examples, and so we should try to see if we can use Euler's theorem to tell us about the answer. Here, the GCD of a and n is equal to 1, and we can compute that phi of n is equal to 40. So if we could determine what this exponent b1 is modulo 40, then we could figure out, as we did in the previous examples, what Graham's number is modulo 100. So the first step here is to try to figure out what the exponent b1 is modulo 40, and we'd like the answer to be a residue class R1 from 0 to 39. Well, now that we can sort of see the path forward, let's reorganize the information to make it clear what we're trying to do. We want to compute Graham's number modulo 100, and we observe that since 3 and 100 are relatively prime, and the Euler phi function of 100 is 40, we should try to compute the exponent b1 modulo 40. Well, the exponent b1 is 3 to a power tower of 3's, which we're going to call b2. And now we can try to apply the same type of observation again. So first of all, notice that 3 and 40 are relatively prime, and that the Euler phi function of 40 is 16. Therefore, in order to compute 3 to the power b2 modulo 40, we'd like to know the exponent b2 modulo 16. Well, now we can apply the same type of reasoning again, this time writing b2 as 3 to a power tower of 3's, noting that 3 and 16 are relatively prime, and that phi of 16 is 8. So now we want to try to compute B3 modulo 8. It's still not clear to me what this number is modulo 8, but I can see that the moduli are getting smaller at every step, and so if I keep going, eventually this process should end. And so, observing that 3 and 8 are relatively prime and that phi of 8 is 4, now we want to know what B4 is modulo 4. Well, we could actually do one more step like this, but here we can determine what this number is modulo 4 pretty easily. To compute B4 modulo 4, just observe that 3 is negative 1 modulo 4, and that whatever this huge exponent is, it's definitely an odd number, because it's 3 to some power. Well, I know that negative 1 to any odd number is just negative 1, so B4 is negative 1 mod 4. Next, I need to work backwards to figure out what B3 is modulo 8, and then what B2 is modulo 16, and then what B1 is modulo 40, and finally I'll be able to determine what Graham's number is modulo 100. Remember, B3 was 3 to the power B4, and I know that B4 is negative 1 modulo 4, so I can write it as 4 times the quotient minus 1. By properties of exponents, remembering that I'm working modulo 8, that's 3 to the 4th power to an integer power times the inverse of 3 modulo 8. Well, 3 to the 4th power is 1 modulo 8, because the Euler phi function of 8 is equal to 4. And the inverse of 3 modulo 8 is just 3, because 3 times 3 is 9, which is 1 mod 8. And so now I've determined that B3 is 3 mod 8. Now I go back and I try to determine B2 modulo 16. Well, since B3 was 3 modulo 8, B2, which is 3 to the B3 power, is 3 to the 8th power to an integer power times 3 cubed. The quantity in the parentheses here is 1 mod 16 because of Euler's theorem, and so I'm left with 3 cubed, or 27, which is 11 mod 16. Next, B1 is 3 to the power B2, which is 16 times an integer plus 11, and so here the problem boils down to computing 3 to the 11th power modulo 40, which is something that my calculator can handle, and it tells me that the answer is 27 modulo 40. And finally, to answer the question, Graham's number is 3 to the power B1, which we've determined is an integer multiple of 40 plus 27. Again, using Euler's theorem, that just turns out to be 3 to the power 27 modulo 100. And even though 3 to the 27 is just a little too big for my calculator, I can compute it pretty quickly by using the square and multiply algorithm, and I find without too much trouble that it's equal to 87 modulo 100. So the answer to my original question is that, even though there's a lot that I haven't told you about Graham's number and there's a lot that nobody knows, we've now shown that the rightmost 2 digits of this number are 87. The next important result that I want to talk about is called the primitive root theorem. This is a very important theorem which was first proved by Gauss, and it gives us a criterion for determining when the multiplicative group of integers modulo n is actually a cyclic group. What it says is that z mod n z times is a cyclic group if and only if the integer n is of one of the following forms: 1, 2, 4, p to the k, or 2 times p to the k, where p is an odd prime and k is a natural number. Please note here that we're talking about the multiplicative group of integers modulo n and not the additive group of integers modulo n. The additive group of integers modulo n is always a cyclic group, and that's something that we've already mentioned before. But the multiplicative group of primitive residue classes modulo n is a cyclic group if and only if n is of one of these forms. Now, when the multiplicative group is a cyclic group, then any residue class which is a generator for the group is called a primitive root modulo n. Just to make sure that we understand the theorem, let's do a couple of easy examples, and then we'll do a more interesting one. So first of all, the primitive root theorem tells us that the group z mod 7z times is a cyclic group because 7 is an odd prime number. So let's try to check this statement by finding a primitive root modulo 7. Of course, the residue class 1 is not going to be a primitive root modulo 7, since 1 to any power is just 1. So it's natural to start by looking at the residue class 2. Well, 2 to the 0 power is 1, and 2 to the first power is 2, and 2 squared is 4, but now 2 cubed is 1, and so it's not difficult to show from this, using for example the division algorithm, that the powers of 2 in this case only generate the 3 residue classes 1, 2, and 4. And since the cardinality of this group is 6, we know that 2 is not a primitive root modulo 7. So now let's look at the residue class 3. We go through and compute the powers of 3, working modulo 7, and we find very easily that the powers of 3 do sweep out all 6 distinct primitive residue classes modulo 7. Therefore, 3 is a generator for this group, which means that 3 is a primitive root modulo 7. Now, it's worth pointing out in this example that 3 is not the only primitive root modulo 7. The residue class 5, which by the way happens to be 3 inverse modulo 7, is also a primitive root modulo 7. But besides 3 and 5, the other 4 residue classes in this group are all not primitive roots modulo 7. Now, another simple example, what can you say about the multiplicative group of integers modulo 9? Well, this time 9 is not an odd prime, but it is the power of an odd prime because it's 3 squared. And so the primitive root theorem tells us that this is actually a cyclic group. Well, this is an example that we saw in our previous video, and we figured out there that the residue class 2 is a generator for this multiplicative group. If you go through all the residue classes in this group, you can figure out pretty quickly that the primitive roots modulo 9 are the residue classes 2 and 5, and that all of the remaining 4 residue classes are not primitive roots modulo 9. Well, now that you have the hang of this, let's look at a more complicated example. In this example, we're working modulo 103, which is an odd prime number, and we're given that 5 is a primitive root modulo 103. To check this at this point would be a little bit of a pain, and we're going to have faster ways of checking things like that later on. But for now, let's just take this as a given of the problem. So, given that 5 is a primitive root modulo 103, how can we find all residue classes x modulo 103, which satisfy the equation x cubed equals 1 modulo 103? Now, this is a polynomial equation, so it has a little different flavor than some of the other modular arithmetic equations that we've solved so far. But solving this particular equation is something that we can do pretty easily using primitive roots. First of all, writing g equals 5, and noting that the order of the multiplicative group of integers modulo 103 is 102, we have, since g is a primitive root, that z mod 103 z times consists of the collection of powers of g, starting from g to the 0 and then going up to g to the 101. Now, g to the 0, of course, is 1, and it's not difficult to show, since the powers of g just cycle around, that g to any integer power is going to be equal to 1 if and only if that integer is an integer multiple of 102. Well, that's the same as saying that that integer n is equal to 0 modulo 102. Now, since every element of z mod 103 z times can be written in the form g to the m, for some m going from 0 up to 101, let's think about what happens when we take an element of this form and then cube it. When we take g to the m and then cube it, we get g to the 3m. And by the comment that we made above, that's going to be equal to 1 modulo 103 if and only if the exponent 3m is equal to 0 modulo 102. Now, we could solve this equation using the ideas that we talked about at the end of the previous video, since the GCD of 3 and 102 divides 0. But in this case, the problem is pretty simple. Since we're only thinking about integers m from 0 up to 101, the only way that 3 times an integer like that could be 0 modulo 102 is if m is one of the 3 integers, 0, 34, or 68. That means that there are going to be exactly 3 solutions to the equation x cubed equals 1 modulo 103. And since g is 5, it's not difficult after a little bit of work to find representatives for all of these residue classes, which lie in the range from 0 to 102. So the 3 solutions modulo 103 are 1, 56, and 46. The final result that I want to talk about is what's called the Chinese remainder theorem, and it's a theorem which tells us about solutions to systems of linear equations modulo different moduli. So let's suppose that you have k different moduli n1 to nk, and that you have k different residue classes a1 to ak modulo all of those moduli. The question is, given this information, can you find an integer x with the property that x is equal to ai modulo ni for every I going from 1 to k? Well, the Chinese remainder theorem says that if the moduli are pairwise relatively prime, which means that any 2 distinct moduli are relatively prime, then there's always an integer x which solves the system of equations, and furthermore, this integer x is unique modulo the product of the moduli. Now, I'd like to give a few examples to make sure that we understand this theorem, and I'd like to also talk about how you actually find integers x that solve systems of equations like this. So for our first example, let's consider the problem of finding the collection of all integers x satisfying the system of equations x equals 7 mod 10 and x equals 3 modulo 21. Since there are only 2 moduli in this case and the GCD of the 2 moduli is 1, the Chinese remainder theorem guarantees that there is a solution x to the system of equations, And furthermore, it also guarantees that this solution is unique modulo the product of n1 and n2. Now, because the moduli here are small, we can find an integer x satisfying this system of equations just by trial and error in this case. So let's go through all the positive integers that are 3 modulo 21, starting from 3 and working our way up. The Chinese remainder theorem tells us that there's going to be at least one integer x which satisfies this system of equations and which is less than 210. And so that means that I'm going to have at most 10 things to check here. So we start with the integer 3, but 3 is not equal to 7 mod 10, so that one is out. And then we go to the next integer, which is 3 mod 21, which is 24. But 24 is not 7 mod 10 either, and so we keep going. And after not too long, we finally find that the integer 87 is 3 modulo 21, and it's also 7 modulo 10. So this one is a winner. Now, because we know that this solution to the system of equations is unique modulo 210, we also know that the set of all solutions is the single residue class 87 modulo 210. Now, in applications, some of the numbers that we work with are much larger than 21 and 10, and so it's desirable to try to find a faster way to compute that residue class x, which is guaranteed by the Chinese remainder theorem. Also, in some applications, we may not actually know what the moduli n1 to nk are, but we still want to try to write down an integer x which satisfies the conclusion of the Chinese remainder theorem. So it would be nice if there's some kind of formula for that integer. Well, it turns out that there is, and in order to describe how to compute this integer x, first let's consider the case of two moduli. When we have two moduli, n1 and n2, which are relatively prime, in order to find the integer x which is guaranteed by the Chinese remainder theorem, we want to start by computing integers m1 and m2 with the properties that m1 is n1 inverse modulo n2, and m2 is n2 inverse modulo n1. Note here that the fact that n1 and n2 are relatively prime guarantees that both of these inverses exist. Also, from our previous video, we know that there's a fast algorithm, the reverse Euclidean algorithm, which allows us to compute the inverse of a primitive residue class modulo any modulus. Now, once we've computed these two integers m1 and m2, it turns out that we can take x to be the integer n1 m1 times a2 plus n2 m2 times a1. In other words, we claim that this integer is going to have the property that it's a1 modulo n1 and that it's a2 modulo n2. Now, to see why that's true, first of all, think about what happens when you consider the right-hand side of this expression modulo n1. Since the first term here is an integer multiple of n1, x mod n1 is just equal to n2 m2 times a1. But since m2 was chosen so that it's equal to n2 inverse modulo n1, n2 m2 is just 1 modulo a1, so this product is equal to a1 modulo n1. Now similarly, if you consider x modulo n2, the second factor disappears and you just get n1 m1 times a2, but because m1 was chosen to be the inverse of n1 modulo n2, this just reduces to a2 modulo n2. That shows that this integer x is a solution to the system of equations in the Chinese remainder theorem. And of course, we can replace x by any other representative for the same residue class modulo the product of n1 and n2. Okay, well, now let's do an example with numbers, just to make sure that we actually know what we're talking about here. So let's try to find an integer solution x to the system of equations x equals a1 mod n1 and x equals a2 mod n2, with n1 equals 15, n2 equals 37, a1 equals 8, and a2 equals 27. Following our recipe, the first thing that we want to try to do is to find an integer m1 with the property that m1 is equal to n1 inverse modulo n2. Now, a lot of times, especially with smaller numbers, there are shortcuts, but just to remind you how we do this in general, when there's not an obvious better way, we just use the reverse Euclidean algorithm. So we start by writing 37 as an integer multiple of 15 plus a remainder, and then we continue until we get down to the point where there's no remainder. Then we back up one step, and we run the reverse Euclidean algorithm to write 1 as an integer linear combination of 15 and 7, and then to substitute in 7 as an integer linear combination of 15 and 37, which tells us how to write 1 as an integer linear combination of 15 and 37. But then, of course, looking at this equation, modulo 37 tells us that 5 is an inverse of 15 modulo 37, so we can take the integer m1 to be 5. However, there's an additional piece of information here, because looking at this equation, modulo 15 also tells us that negative 2 is an inverse of 37 modulo 15. So we also get from the same calculation that we can take m2 to be negative 2. This is a benefit of using the reverse Euclidean algorithm for this calculation. Once you've written 1 as a linear combination of n1 and n2, it's always going to tell you the values of both m1 and m2. Well, now that we've computed m1 and m2 with the properties that we want, we can take x to be n1 times m1 times a2 plus n2 times m2 times a1, and we know that this integer x is going to be a solution to our simultaneous system of equations. Now, this integer x turns out to be bigger than the product of n1 and n2, and although that's not really a problem, if I were trying to find the smallest positive integer x which is a solution to the system of equations, then taking into account the fact that I can pick any other residue class for this integer modulo n1 times n2, I find that the smallest positive integer which is a solution to the system of equations is 323. Now, before we move on, I just want to make a small comment. In the example that we just did, we observed that when you find m1 using the reverse Euclidean algorithm, it also tells you right away what m2 is. Well, there are lots of times when we may be able to tell what m1 is without using the reverse Euclidean algorithm. And so the comment that I want to make is that when you know n1 inverse modulo n2, no matter how you find it, there's always a shortcut to computing n2 inverse modulo n1. First of all, since n1 times m1 is 1 modulo n2 by definition, if I multiply both sides of this equation by negative 1, I find that n1 times negative m1 is negative 1 modulo n2. Writing out what this means, it means that n1 times negative m1 plus 1 is n2 times k for some integer k. But now the thing to notice about this equation is that if I think about it modulo n1, the first term on the left-hand side here disappears, and I'm just left with n2k equals 1 modulo n1. In other words, that integer k is an inverse of n2 modulo n1. But since I know all of the other integers n1, m1, and n2, I can solve directly for k, and I find that k is n1 times negative m1 plus 1 divided by n2. This gives an easy way to find an inverse of n2 modulo n1 when you already know an inverse of n1 modulo n2. Next, let's talk about how to find an integer x satisfying the conclusion of the Chinese remainder theorem when you have more than two moduli. Well, here the key is to proceed inductively. So first of all, you use the algorithm that we already talked about to solve your first two equations and to find an integer x1, which is a1 mod n1 and a2 mod n2. Note also that this integer is unique modulo the product of these moduli, so that what I'm about to say next makes sense. Now, once you've found an integer like this, what you want to do is throw in the third modulus and find an integer x2, which is equal to x1 modulo n1 times n2, and which is equal to a3 modulo n3. Notice that the fact that x2 is x1 modulo n1 n2 guarantees that x2 satisfies both of the first equations, modulo n1 and modulo n2. And so now, of course, the recipe is just to keep going, throwing in one modulus at a time, until you get down to the very last modulus. And once you've done that, you will have found an integer, x, which satisfies all of the equations in your system of equations. Now, this is just a lot more work, but it's not a lot harder than the case when k is 2. So I'm going to give you an example, but I'm going to go through it kind of quickly. Here, let's find an integer x which satisfies the system of four equations x equals ai modulo ni for I going from 1 to 4. You can check for yourself that all of these moduli are pairwise relatively prime, and that is actually important to guarantee that a solution exists. Well, first of all, I'll solve the first two equations, x1 equals 2 mod 3 and x1 equals 3 mod 5. And because the numbers are so small here, I can just guess a solution, and I find that x1 equals 8 works. Now I want to find an integer x2 which satisfies the equation x2 equals 8 modulo 15, which is the product of the first two moduli, and x2 equals 27 modulo 37, which is the third equation that I'm trying to solve. Well, the good news here is that we just now did this one. That was the result from the previous example, and we found that we can take x2 to be 323. And so now for the final step, I need to find an integer x3, which is equal to 323 modulo the product of the first three moduli, and which is equal to 81 modulo the last modulus. Now, in order to do this, what I want to do first is to compute the inverse of 555 modulo 101. And I could do this using the reverse Euclidean algorithm, but in this case I can do it a little bit faster just by using a trick. So 555 is equal to 50 modulo 101. And 2 times 50 is 100, which is negative 1 modulo 101. So that tells me that the inverse of 50 is negative 2 modulo 101. And now I'm done with that part, and I can take my m1 here to be negative 2. To compute the inverse of 101 modulo 555, I can use the shortcut that I just talked about. Since I know that 555 times 2 is negative 1 modulo 101, I know that 555 times 2 plus 1 is 101 times k for some integer k, which is therefore the inverse of 101 modulo 555. And by direct computation here, I find that k is equal to 11, so that's the m2 that I'm looking for. Now, of course, I have all of the pieces of information that I have to complete the story, and I can compute an integer x which is a solution to all 4 of my equations. That integer x is unique modulo the product of all the moduli, and so once I work this out, I find that I can take x to be 44,723, so that that value of x is a representative for the residue class modulo the product of all of these moduli, which is the set of solutions to my system of equations. Okay, well, I want to conclude with a slightly more interesting example. So in this example, let's take n to be 605, and let's try to find all integers x modulo n, which satisfy the equation x squared equals 1 modulo n. Now you might think that if x squared is 1 mod n, then x has to be plus or minus 1 mod n. And while that is true if n is a prime power, it's not true in general if n is a composite number. And so you have to be a little careful here. The key observation here is to notice that the system of equations x squared equals 1 mod 5 and x squared equals 1 mod 11 squared has a unique solution modulo the product of those moduli by the Chinese remainder theorem. And so the strategy is to try to solve each of these equations modulo 5 and modulo 11 squared, and then combine all pairs of solutions into solutions modulo n using the Chinese remainder theorem. Now the reason why this is a good strategy is because it's a lot easier to solve the equation x squared equals 1 modulo a prime power than it is to solve the equation x squared equals 1 modulo a composite number directly. And let me try to first explain why that's true. The important fact that we need here is that if p is an odd prime number, so not equal to 2, and if k is any natural number, then the only solutions to the equation x squared equals 1 modulo p to the k are x equals plus or minus 1 modulo p to the k. Now, I mentioned this just a second ago, but to see why it's true, let's suppose that x is an integer with the property that x squared equals 1 modulo p to the k. Of course, that means that p to the k divides x squared minus 1, and since x squared minus 1 factors as x minus 1 times x plus 1, that guarantees that p to the k has to divide x minus 1 or x plus 1. Now the justification for this last step uses the fact that p is a prime bigger than or equal to 3, so it doesn't work when p is 2. But if p is a prime bigger than or equal to 3, then it can't divide both of the numbers x minus 1 and x plus 1, since the difference between those two numbers is only 2. Therefore, if p to the k divides x squared minus 1, then p to the k has to divide either x minus 1 or x plus 1. And that's exactly the same as saying that x has to be 1 or negative 1 modulo p to the k. Therefore, that proves this fact that for odd prime powers, the only solutions to the equation x squared equals 1 mod p to the k are plus and minus 1 modulo p to the k. Now, using that fact, we know that there are only two solutions to each of the equations a1 squared equals 1 mod 5 and a2 squared equals 1 mod 121. And so, since there are two choices for a1 mod 5 and two choices for a2 mod 121, there are four different pairs a1, a2 that we need to consider. For each of those pairs, any integer x which satisfies the equation x equals a1 mod 5 and x equals a2 mod 121 will be a solution to our equation x squared equals 1 mod n. So now all we have to do is go through each one of the four cases and solve the corresponding system of simultaneous equations. Here are the four different cases, and each of the four cases can be solved using the Chinese remainder theorem. It's pretty easy to see that the only integer x modulo n, which is 1 mod 5 and 1 mod 121, is 1 mod n. And similarly, that the only integer x which is negative 1 mod 5 and negative 1 mod 121 is also negative 1 mod n, which is 604 mod n. Now, because these numbers are small, to solve the remaining two equations, you can just guess the answers. But in general, for bigger numbers, you would use the method that we talked about in our previous examples. Well, in any case, it turns out that there are four solutions modulo 605 to the equation x squared equals 1, And the four solutions are 1, 241, 364, and 604 modulo 605. That's the end of this video. Thank you for watching. In the next video, we're going to move back to the main line of group theory and talk about subgroups.